So next we'll see about the classification of the memory allocation. So your basically memory allocation is nothing but allocating memory for the process, that is how your operating system saves or stores the process in the main memory. So basically it can be the memory location, it can be contiguous or it can be non-contiguous. Okay, so then again contiguous memory location is again classified into static or fixed partitioning, then again variable or dynamic partitioning. So static or the fixed partitioning, again it is divided into two types, that is fixed size partitioning, or it is also called as equal sized partitioning, and variable sized partitioning. So we will see all these things, right? So first we'll talk about contiguous, what is contiguous and non-contiguous memory allocation. Then I'll talk about this one, fixed or static partitioning. Then I'll talk about these two things. So let us see one by one. Okay, so the first one is contiguous and non-contiguous memory allocation. So contiguous memory allocation, it means your single block of memory is allocated to a process. It should be continuous. Okay, say for example, if suppose this is our main memory, okay, you have operating system here, then continuous means your process would be kept like this, P1, then P2, something like this, and again the address, it should be continuous. Say suppose it is 0 and it is 100, it is 150, it is 200, something like this. So from 101 to 149 continuously process P1 is kept, then from 150 to 199 process P2 is kept, something like this. So that is your contiguous memory allocation. The process would be kept continuously in your main memory. Fine. Okay, then non-contiguous, it is the opposite of contiguous, right? What does that mean? So it is something like this. If suppose this is your main memory, this is operating system, then say some part of process P1 is kept in this location, say P2 is here, again P1 is there, again you have P2. That means the process are not kept continuously in the main memory. Fine. So if suppose say P1, the size of the process P1 is 5 MB, okay, so all that 5 MB is kept in one single block, okay, in the continuous memory allocation. So in the non-contiguous memory allocation, if suppose P1, I say it is of the size of P1 is 5 MB, then in non-contiguous what will happen? Say suppose 3 MB is kept in one location, again 2 MB is kept in another location. So this is your non-contiguous memory allocation. Fine. Next, we have seen this contiguous and what is non-contiguous. Fine. Now I'll talk about this fixed or static partitioning. Okay. Apart from that, okay, once this is done, I'll talk about these two types. Then we'll come to this dynamic partitioning. So now we'll talk about this fixed or static partitioning. Okay. So here in the fixed or static partitioning, what will happen is the number of partitions in the main memory is fixed. I'll draw the main memory so that you understand it better. Okay, if suppose this is your main memory, operating system software is kept here, then what will happen is this partitions, whatever you can see, right, this will be fixed. Okay, this is your operating system from some location to some location, then whatever the user process the free space is there, that would be partitioned or divided into multiple groups, or basically these all things we call it as a whole. This is one whole, this is another whole, something like this. Okay, these are called as either partitions or wholes or fragments. Okay, so partitions, fragments and wholes are one and the same. I'll write here wholes, fragments, then partition. All these things means the same. Okay, your main memory is divided or partitioned into a number of fixed size parts or wholes or fragments. So the size of the partition, this one, okay, the size of this partition, it may be either fixed or variable. Again, when this partitioning is done is like during your system configuration, whenever your system is getting built, at that time this configuration is done. Okay, so Now let us talk about your two types in your fixed partitioning, that is fixed sized or equal sized partitioning and variable sized partitioning. So first I'll talk about this fixed size partitioning. Okay, so your fixed size is nothing but, say suppose this is our main memory. Okay, we have operating system here. Then I said your user process, this free space is divided into multiple partitions or holes, right? So here let me say if we have four partitions of the main memory wherein your process can be kept. So here this fixed size or equal sized partitioning, it means each partition is of fixed size. That means, say suppose this is your first part. Okay, this is first part, this is second part, this is third, and the fourth part, and all these four parts are of fixed size, say 5 MB. Fine, all of these are of fixed size 5 MB. Maximum you can keep a process of size 5 MB in this particular whole or the fragment. Okay, so this is nothing but your fixed sized partitioning. Now I'll talk about variable sized partitioning. If suppose this is your main memory, then you have fixed parts. The partition will not be, variable size. The parts would be fixed, but it is of variable size. Say suppose if this is your first part, second, third, and fourth, that means your first part, say it is of 5 MB. Maximum capacity of this part is 5 MB. The maximum capacity of this particular thing, this second part, is 10 MB. Then the maximum capacity of the third part is 3 MB, and say suppose capacity of this fourth part is 15 MB. Okay, so this is your fixed size and variable size partitioning. So in the fixed size, what will happen? Your user process space is divided into multiple number of partitions, and the size of each partition is fixed, that is 5 MB, 10 MB, or whatever it is, but it is same for all the process. But in the variable size partitioning, what will happen? You will have the user space divided into multiple parts, but each part will be of different size or variable size. Okay. So now let us take either this fixed size or variable size partitioning, and then we'll understand the advantages and disadvantages of this thing. Okay. So say suppose this is your main memory. Okay, and say operating system is here, and say suppose we have 5 partitions, 1 2 3 4. Let me draw one more. Okay, say suppose this is your main memory and OS is kept here, and we have 5 partitions. Say these are all of variable sized. Okay, say suppose this partition, okay, this partition is of 5 MB, this partition is of 10 MB. Okay, this is of 15 MB. The fourth partition is of say 3 MB, and the fifth partition is of say 9 MB. Okay, that means at the same time we can only keep 5 processes in this main memory. Why 5 processes? Because we have only 5 parts, so each part would be occupied by each process. Okay, so say suppose now we have 5 processes in the system. Say process P1, P2, P3, P4, and P5. Okay, we have 5 processes in the system, and the size of process P1 is 3 MB, size of process P2 is 2 MB, P3 size is 10 MB, P4 size is 1 MB, and P5 size is 5 MB. Okay, now these processes have to be kept in this main memory continuously. So why? Because we are talking about continuous memory allocation, and in that we are talking about fixed partitioning. Okay, the partition here, it can be fixed sized or variable sized. For your example, I have taken variable sized. You can see here, right? So say suppose P1 is 3 MB, right? But why do you keep this P1 in the first partition? So what is the size of that partition? It is 5 MB. right? So process P1 is kept in this particular partition or the fragment. So out of 5 MB, your process P1, which requires only 3 MB, is kept here. That means 5 minus 3, that is 2. You have wasted 2 MB. Okay, I'll write here 2W. That means 2 MB has been wasted by process P1. Why it has wasted? Your process size is 3 MB here, but the size of this partition is 5 MB. So 2 MB you have wasted. Then we have process P2, which is of 2 MB, right? But as you can see here, 2 MB has been wasted. So you might say that this process P2, which is of 2 MB, you can keep here in the same location or in the same part. So it cannot be done. Why it cannot be done? Why? Because we are using, or this partition, it already has P1, right? P1 process, and it is continuously present. So each fragment or each hole can contain only one process. Getting it? That's why your process P2 would be kept in the next fragment or the next hole. So how much MB is wasted by this process P2? So size of this fragment is 10 MB and your P2 requires only 2 MB, right? 10 minus 2, that means 8 MB is wasted by your process P2. Okay. Next we have process P3, which will be kept in the third location. I'll write something like this, P3. Okay, what is the size of P3? 10, right? 15 minus 10. So 5 MB is wasted. I'll write like this. 5 MB is wasted by P3. P4, it requires 1 MB, but it has 3 MB fragment here. So P4 would be kept here. And 3 minus 1, 2 MB is again wasted. P5, it requires 5 MB. 9 minus 5, 4 MB is wasted by your P5. Okay, I'll write P5 here. So as we have seen here, altogether how much these 5 process, say suppose how much these memory have been wasted by these 5 process. So you can calculate each process how many MB it has wasted. P1 it has wasted 2 MB, then P2 it has wasted 8 MB, P3 it has wasted 5 MB, then P4 2 wastage and P5 4 wastage. 2 plus 4. Altogether how much? So your 5 process have wasted 21 MB of the memory, right? So here we had seen one thing, right? So when process P1 it was kept here in the first fragment, so the 2 MB was wastage here, but that was not allocated to P2. Why? Because P1 is already present in that particular location, in that fragment, which is continuous. So you cannot allocate any other process in the same fragment, right? So even if you take the partition with a fixed size, like each of 5 MB, then also you will have this memory wastage. So what is the advantage of this one? Like your fixed partitioning. So it is very easy to implement this approach, but there are many disadvantages of this one. So the first disadvantage is, I'll write here, it is internal fragmentation. Okay, so first is internal fragmentation. So what is this internal fragmentation? We'll have a separate topic about fragmentation. We'll talk that detailed, but here have a basic understanding of what is internal fragmentation. Okay, so it is nothing but in your fixed partition, if you allocate memory for a process and there is a possibility that some memory will be wasted. So why the name internal there? Because the memory wastage occurred inside or internally to your fragment or partition or whole. So we have seen, right? I'll show you once again. So here 2 MB of wastage is there. So this 2 MB wastage is inside this fragment or inside that particular hole. So that we call it as internal fragmentation. So we could have kept any other process of 2 MB there, but you cannot keep. So that is the problem. So that is your internal fragmentation. If suppose if you take P4 process, so what is the thing? P4 required only 1 MB, right? But the size of the fragment is 3 MB. So out of 3, only 1 MB is used. That means 2 MB wastage is there. Now this 2 MB wastage, we call it as internal fragmentation. Okay, fine. So the second disadvantage of this fixed partitioning is that limitation on the size of your process. So say suppose you want to execute a process with 50 MB. So then it is not possible with your fixed partitioning. Why? Because even if you have a process of 50 MB and say suppose your fragments are of 5 MB, 10 MB, 20 MB like this, you cannot execute your process which is of higher size. Okay, the next disadvantage here is limitation on number of process. That means how many partitions are there in the main memory, only those many process can be allocated and executed. See suppose this one, right? So we have only 4 partition here, right? Or if you consider this diagram, 5 partitions are there. So that means at a time only, or at one particular time you can execute only 4, or if this is the case, you can parallelly execute or simultaneously execute 4 process. If this is the diagram, then maximum up to only 5 process can be executed simultaneously. So apart from that, we have one more disadvantage, which is called as external fragmentation. Okay, so internal fragmentation is also disadvantage, external fragmentation is also disadvantage. So I'll give you the example for this one. Say suppose you have in the main memory you have 4 process. Okay, say suppose there are 4 partitions, right? So say suppose P1 is kept here, and this is 5 MB, this partition size is 5 MB, this is 10 MB, this is 15 MB, and this is 3 MB. Okay, wait, and say suppose we have, I'll take the same example, right? And this is of 9 MB. That means 5 processes are there in the system: P1, P2, P3, P4, and this is P5, right? So what is the wastage P1 did was, I am basically drawing the same diagram, this diagram, in the next slide. Okay, so 2 MB wasted by P1, P2 wasted 8 MB, P3 wasted 5, this wasted how much, 2 MB, and P5 it has wasted 4 MB, right? That means altogether 21 MB was wasted. Alright, 21 MB wastage, okay, by the process. Now say suppose you have another process P6, okay, it wants to get executed, and say suppose the size of P6 is 20 MB. Okay, size of this process P6 is 20 MB. So now check whether you can store this P6 process anywhere in your main memory. Okay, so we have 5 partitions, that means only 5 process can be there, but the wastage of done by the 5 process is 21 MB. You have one more process coming into picture which is of 20 MB. That means out of 21 you can keep 20 MB, right? You can keep this process in the main memory, but you cannot keep it. Why you cannot keep P6? Why? Because even if the total free space or the wasted space is 21 MB, it is not contiguous. We are talking about contiguous memory allocation, remember? So if the 21 MB was it was contiguous, like suppose it was here, it was contiguous, then we could have kept P6 here. But in our case, the 21 MB is not contiguous. 2 MB is somewhere, 8 MB is somewhere, 4 MB is somewhere, so it is not contiguous, right? So you cannot keep P6 into the main memory. Now that is your external fragmentation. That means even if you have total number of empty space or wastage space in your main memory, you cannot keep any other process which requires that memory. Why? Because it is not contiguous. So that is your external fragmentation. Apart from that, the last disadvantage of your fixed partitioning is that degree of multi-programming will be reduced. That means simultaneously you cannot execute more processes. Why? Because the partitions are fixed. If you have 5 partitions, you can only execute 5 processes. Fine. So this is about your fixed partitioning. In the fixed partitioning, we have seen fixed size and variable sized partitioning. Okay. Next, we'll talk about memory allocation algorithms or the strategies which we need to keep in mind. How, making use of these algorithms, we can keep the process in the main memory. So in the memory allocation algorithms or the strategies, we have three types. So first is the first fit, then it is best fit, then the worst fit. So I'll give you example and then I'll talk about what is first fit, best fit and worst fit in this slide. So the first one is first fit. Okay, so how this strategy works, let us see. First fit, say suppose everything I'll draw here. If this is your main memory and you have operating system here, say suppose there are three partitions. Okay, it is again under your fixed partitioning. Okay, and these partition size are either fixed or variable. Okay, so we'll consider variable itself. Fine, the size of this first partition is say 10 MB, second partition is 15 MB, and the third partition is say suppose 30 MB. Okay, now we have process P1, P2 and P3. The size of process P1 is 9 MB, P2 is 25 MB and P3 is 10 MB. So your first fit strategy or the algorithm, it says that you have to allocate memory to the process such that the first hole that is big enough you allocate it to the process. Okay, allocate the first hole or the fragment. Okay, this particular thing, blank space you can see here, right? It is called as fragment or hole or partition. So your first fit strategy, it says allocate the first hole that is big enough. So say suppose we have these three process. P1 is 9 MB, right? It needs 9 MB. So first what will happen is basically the entire this user space process, it is searched by the system. That means all the whatever are the free spaces would be searched by your system. So as per your first fit, this process P1, it requires 9 MB. So the search typically begins from the beginning. Okay, so it says first fit, it says allocate the first hole that is big enough. So P1 is of 9 MB and the first hole whatever we get is of 10 MB. So can we keep 9 MB in the 10 MB fragment? Yes, we can keep, right? So keep the process P1 in the first hole. Okay. Next, you have process P2 which is of 25 MB. Now again, you have to search for the free space in the user process. So now the searching, it can either begin from the first point or at the start of your memory, or it can be started from where you have last stopped your first fit search. Either ways you can do. Okay, so now this you can just check here. Process P2 is of 25 MB and second free space is of 15 MB. So you cannot keep here, right, 15 MB because the process size is more. You leave this one, then check for the third hole. So what is the size of this one? It is 30 MB and process P2 is of 25 MB, so that you can keep this process P2 here. Okay, now the last one is P3. As we have only one partition, just keep P3 here. Okay, so if suppose say there were 5 partitions and your P3 was the last process, then what you have to do? You have to check for all the 3 process there or all the 3 allocations there. Okay, so next we'll talk about the best fit strategy. Best fit strategy. Okay, so let me draw the diagram. Say suppose I'll take the same. The first part is of 10 MB, 15 MB the second one, and the third one is 5 MB. And again say suppose we have process P1, P2, P3 of 9 MB, 4 MB, and this is 10 MB. This is 4 MB, right? So how do you allocate these 3 processes into the main memory using best fit strategy? So your best fit strategy, it says allocate smallest hole that is big enough for the process. So your best fit strategy, it says allocate smallest hole that is big enough for the process. So first, what you have to do, you have to scan all the holes which are present in the main memory. Okay, the holes or the fragments are of 10 MB, 15 MB and 5 MB. So which among these is the lowest? You have to check, right? So compare this P1, okay, with which has the size as 9 MB, right? So can you keep this P1 in the 10 MB slot? Yes, you can keep. Can you keep it in the 15 MB slot? Yes, you can still keep. But can you keep it in the 5 MB slot? So your P1 cannot be kept here. Why? Because size of the fragment is 5 MB, size of the process is 9 MB, which is greater. Now you have two more things, right? 9 MB, it can be kept in 10 MB as well, and this slot 15 MB as well. So according to your best fit strategy, it says allocate smallest hole that is big enough. So what is smallest among 10 and 15? It is 10, right? So you keep your process P1 in this 10 MB block. Okay. Next, you have P2, which is of 4 MB. This P2 4 MB, it can be accommodated in this 15 MB slot as well as 5 MB slot. But which is smallest among 15 and 5? It is 5, right? So keep your P2 in this block. The last one is P3, which is of 10 MB. Basically you can keep it here as we have only one slot, right? Okay, so this is about your best fit. Okay, next we'll talk about worst fit. Fine, let me draw the diagram. Again, say this first slot is of 1 MB, second slot is of 10 MB, and the third one is 5 MB. Okay, now say suppose again I'll consider three process P1, P2 and P3. P1 is of 9 MB, P2 is of 4 MB and P3 is of 5 MB. Now this worst fit strategy, it is opposite to your best fit strategy. So your worst fit strategy, it says allocate the largest hole to the process. Okay, now you have process P1, P2, P3. Those things have to be kept in this memory locations or the holes according to this worst fit strategy. How can we do this one? So first consider process P1, which requires 9 MB, right? So can you keep 9 MB in 1 MB or 5 MB? No, right? The largest hole. Scan all the, first thing, your system scans all the available holes in the main memory. Okay, so your P1, it can be kept only in this hole, which is largest, right? So keep P1 here. Okay, how much memory is wasted? 1 MB is wasted here. Then you have P2 process, which is of 4 MB. The size of process is 4 MB. So you search again from the starting, right? 1 MB slot is there, 5 MB slot is there. Of course, you cannot keep here, so you better keep here, right? P2 in the 5 MB slot. Again, we have 1 MB shortage here, right? Or 1 MB is wasted by your process P2. Basically you have to find out the largest hole. Okay, so the last one is P3. Now it requires 5 MB, right? So can you keep 5 MB in this 1 MB? This is the only left out slot here, but you cannot still keep your 5 MB in this one, right? So we do not have any large hole or the fragment in the main memory. So your P3 process, it has to wait till any other process terminates. After terminating, if suppose any of the slot becomes free, which is largest, then your P3 can be executed or kept in that slot and then can be executed. Fine. So this is about your memory allocation algorithms or strategies. First fit, best fit and worst fit. Fine. That's it for today. We'll conclude our session. Thank you.